I'm going to describe, hopefully to you, the approach that we have developed in our paper based on the formalism of Coadjoint orbit to tackle the problem of Fermi liquid. But first, let me remind you what we have discussed last time, some peculiar features of Landau's Fermi liquid theory are that Landau's Fermi liquid theory is formulated in terms of liquid theory is formulated as a classical theory in terms of classical equation of motion on the distribution function f x of p. I'm not going to write down the equation of motion, but one feature of this equation of motion is that the Fermi surface sharpness is preserved over time. That is, if we start the evolution with a state in which the distribution function is 1 inside some region in phase space, so x and p, and then some x, then this property is that there is a sharp surface that separates f equals 1 region from the f equals 0 region is preserved over time. In some sense, then, the Landau's Fermi liquid theory can be written as an equation that says the shape of that region, restricted ourselves to the solution to the equation that preserves these properties, that has this sharpness property. The equation, roughly speaking, is this the derivative, time derivative of the shape is some functional of the shape itself. Okay. So very symbolically, this is the equation of Landau's Fermi liquid theory. And one, we also last time talked about conservation laws, and one of the quantity that is conserved is the total energy. So the total energy is also some functional that depends on the shape of the Fermi surface. And here, let me write it down in more detail. In Landau's Fermi liquid theory, it is integral over dx dp of epsilon p0, the change of the distribution function, plus 1/2 of some integral over 2 momenta, p1, p2, now some function of p1 and p2, delta f xp1, delta f of xp2. In Landau's Fermi liquid theory, this delta f can be any function, but here we are restricting ourselves to f that is either 0 or 1. So that should be thought of as an expansion over the deviation of the, so it's some kind of this expansion is expansion over the deviation of the shape of the Fermi surface from the shape it has in the ground state.
So you want to restrict from now on to delta f equals 0, 1?
Yeah, I'm going to restrict myself from now on to delta f equals 0 or 1.
Or minus 1.
There is no minus 1.
Delta f is?
No, sorry, f itself is equal to either 0 or 1. Now, there's two problems that one can envision here. First problem is how to parameterize the shape in a way that makes the formalism simple. It's a technical problem. One simple, most straightforward approach would be to start with the round Fermi surface and then introduce some height function u of x. Say, suppose I am in 2 dimension, two spatial dimension. The Fermi surface. If it deviates not too much from the original round Fermi surface, its shape can be parameterized by a height function, which is a function now of the angle theta, and it would be a function of x as well. So this is px, py plane. We will not use this to run ahead. We will use a different parameterization that turned out to be more convenient. But the second problem is more fundamental. That is how to let's see, what is the symplectic structure in the space of all these shapes. And let me elaborate on the contents of the second question. If we have a system with the Hamiltonians, it's not sufficient to know the Hamiltonian to know the equation of motion. We also need to know what are the pairs of canonically conjugate variables. So in the usual Hamiltonian mechanics, we have a Hamiltonian that is a function of the generalized coordinate qa and generalized momenta pa. Let's say a runs from 1 to n index. The equation of motion that we write qa dot equal dh over dpa and pa dot equal dh minus dh over dqa know something about these coordinates. They are not like random coordinates, but they form canonically conjugate pairs. This equation can be thought of as the equation that follows from an action principle. So an action that leads to this equation is, you can write this as dp pa qa dot minus h of qa pa. Here let me write sum over a pa qa dot. Okay, so the first term then is a term with one derivative and can be written as just integral of p dq, sum over a pa dqa. Thinking about both p and q's as function of t. Okay. So this first term can be then written as an integral of a, this is a one form, and the more general version of this Hamiltonian dynamics would involve not this particular one form, but a more general one form. And let me let us consider the more general case. So the more general dynamics, Hamiltonian dynamics, can be introduced this way. Again, if there is any question during a talk, please interrupt me at any time. More general dynamics, we would have a set of phase space coordinate psi of a, and here I'm not distinguishing any, not breaking them into pairs of momenta and coordinates. But I'm going to write the following action: S equal integral dt, and then I have here the one form which I write like this: a capital, so a of a psi. Here is the set of n function of this phase space coordinates psi a dot minus h of psi. So you can think about this, this case as a particular case where only half of the function a are not equal to 0. And this function a that has an index that corresponds to the qa would be equal to pa. Right, here we have a more general function, and if you derive the equation of motion using standard variational calculation, we find the following equation of motion. You will find the equation of motion omega ab psi b dot equal dh over d psi of a, where omega ab is equal dA ab minus dB a of a. So omega ab is like if a is if we consider a as a gauge potential, then omega is the gauge field. Right, and as such, omega ab is a function of xi. All of that is a function of xi. Moreover, as a gauge field, it's antisymmetric. And it has a zero derivative as a two form. So d of omega equal to 0, or in component d of omega dA of omega bc is equal to 0. The equation of motion depends only on the gauge potential, gauge field omega ab, but not on the gauge potential itself. And one can see that, one can relate that with the symmetry of the action with respect to gauge transformation in phase space. We can replace any function of xi by a function, the same function, plus derivative of another function, the a of lambda. And one can check that the action is changes only by a total time derivative of that function lambda. And that, that means that the equation of motion of the theory with this a or with that a are the same, as we see by explicit calculation here. So this omega ab is symplectic two form that determine the dynamics of the system in addition to the Hamiltonian. If we have the omega ab two form and the Hamiltonian, then the classical dynamics of our system is completely defined.
So you assume phase space is even dimensional and the determinant is regular?
Yeah, otherwise the equation cannot be inverted. Yeah, I assume omega ab is non-degenerate two form. So this also, in parentheses, we are not going to use this, but there is a way to think about the same system using the usual Hamiltonian, the formalism with Poisson bracket. We can write the equation of motion as omega a sigma a dot equal to the Poisson bracket between sigma a and the Hamiltonian, and the Poisson bracket between the two canonical coordinate. Psi a will be the invert matrix of the matrix omega ab written here. So it's like omega minus 1 ab. up to a sign, omega maybe -1. So there is a correspondence between the notion of Poisson general Poisson bracket and the symplectic two form.
And as you know, Lagrange had introduced before Poisson omega AB itself. They are called Lagrange brackets.
Lagrange bracket. I think, yeah, I heard about that, but yeah, I see. Thank you. I know only 3 people, which now I know 3 people whose name is attached to a certain kind of bracket. Maybe there are more. This used to be, we used to say Poisson, Dirac.
Yes, it's Spires.
Byers bracket. Yeah, so. Okay, so 4. Yes. So the problem here in our Fermi liquid problem is, how do we think about, how do we know what is the correct symplectic form that one should use in the multi-dimensional, infinite dimensional space of all possible shape of the Fermi surface. And that problem we are going to solve fully in this lecture. And to solve that, I'm going to use the method called the method of Coadjoint orbit. So I will have to spend some time introducing several mathematical notions that may be familiar to many physicists, but they were not familiar to me before I worked on this problem, and so I assume for some people, this mathematical introduction will be useful as well.
You will take the shapes as function of x, or x is fixed here as function of the angle?
The shape is a function of x and the angle.
It will be important for that.
It will play a role, yes. But on the other hand, it will comes out quite naturally that the function that parameterizes the shape will be a function of x and the position on the Fermi surface. In 2 dimensions would be theta. But it will appear later on why we need exactly that function of exactly that many parameters for our formalism.
Can I ask a question? So you put it, what is the symplectic structure on the space? I'm sure there are many different symplectic structures.
The symplectic structure for which this equation is the correct one.
Yeah, but what is the criterion of correctness?
That's written by Landau.
But I thought the goal was to understand why Landau was correct. If we just need to reproduce his equation, yeah, I'm sure we can do it, but are we going to...
We are going to argue that it is a correct one, yeah, that Landau is the correct one.
We have another criterion of correctness.
Yeah, but that one is probably weaker than the criterion that Landau is always right. We will see. Yeah, it's not always right, but yeah. Sure, yeah, and there are some wrong papers as well, as you know. Okay, so I'm going to give you an introduction to the method of Coadjoint orbit, but in particular adjusted to this problem. So the first, there is some things that we all know, and then something that are less known. The first thing that I think of everybody knows is the notion of canonical transformation.
And the group, because, okay, there will be a group. This is a group of volume preserving things.
It's a group more than volume preserving in higher dimension. In 2 dimensions, this canonical transformation is, so let me define this. So let me write down this infinitesimal first. version. This is the transformation from the phase space coordinates x and p to another phase space coordinates, and I call x and p, such that the Poisson bracket is preserved. The infinitesimal form of this is the following: x goes to capital X equal x minus epsilon df over dp, and p goes to capital P equal p plus epsilon df over dx, where
what is what we called q before, because there are various x's.
There are q before, but yeah, but you can.
Newtonian x. It's not the x of the Landau theory.
Eventually, it's going to be that x. Yeah, but let's.
So because there's some f, also f appears. Is this f the same as Landau f, or is it something else?
It's not the same as Landau f. It's some function of x and p.
So this section is completely independent.
The section, let's make it right now. Let's forget about Landau's Fermi liquid theory for a moment and talk about canonical. The group. So basically, I want the outline is the following. So first, I want to talk about the group of canonical transformation. That one. Then I will remind you about something that can be done independently of this group, is the notion of adjoint and coadjoint representation. I want to talk about, so this part is independent of the particular group, the coadjoint orbit, and then the notion of Kirillov form or KS form. So let's first talk about this particular group first, and then.
KKS means Kirillov-Kostant-Souriau.
Kostant-Souriau form, yeah. Kirillov-Kostant-Souriau form, yes. Okay, so this is the transformation, which can be written this way. It can be written at x minus plus epsilon times the Poisson bracket of the function f at x.
Are you still assuming that your space is finite dimensional or not?
It's finite dimensional, yeah, 3 dimensional in particular.
I mean x and p.
And x and p here. It's coordinates and momenta of a single particle in finite dimensional space, in particular in 3 dimensional space. So this is p plus epsilon f x at p. So basically one can define the notion of this canonical transformation, and it's easy to check that this infinitesimal transformation form a closed algebra where the commutator in the algebra of 2 transformation parameterized by 2 functions f1 and f2 is equal to the Poisson bracket between f1 and f2. So let me write this way: f1, f2. The commutator, in the sense we take this transformation and then commute it, would give us another canonical, infinitesimal canonical transformation, but with the parameter equal to the Poisson bracket of the f2 function f1 and f2.
With the sign plus?
I think with the sign plus. I tried to check yesterday that
the commutator, because sometimes the sign becomes minus subjectively.
Yeah, I think I choose the sign here so that it's plus, but I think it's plus at the end. But I don't. For me, this notation is more convenient. this choice.
Sorry, is it necessary to use this Darboux coordinate x and t, or can we do it just like more covariantly?
Well, maybe in some context later on it's going to be more, if I'm doing Fermi liquid in flat space, this is sufficient. But I think I'm going to restrict myself to that. But in principle, I think there's no reason why one should. It's just to illustrate that there is a concrete algebra. Before that, one can also define the group of canonical transformation by exponentiating this algebra. So these are, if one think about this as a kind of Hamiltonian evolution using the function f, or more precisely minus f, as the Hamiltonian during infinitesimal time epsilon, then the elements of the canonical transformation group will be to evolve this using this equation, but in a unit time. So then one would, in finite time, one would get elements of the canonical transformation group. Okay, any question so far? I think that's all that we need right now. And let's me then start talking about the notions of representations, the adjoint and coadjoint representation. So the representation here, we would understand it as a map that would take one, say, a representation of a Lie algebra is a way to represent each generator of the Lie algebra as a matrix, so that the commutator becomes commutator of the two matrices. For any Lie algebra, there is an adjoint representation. So it works like this. So I need to, sometimes the notation will be a little bit mathematical. So this is the representation where each of elements, so if I have an element of the Lie algebra, which for my purpose, the element of the Lie algebra will be denoted as a capital F or G vector, is put into a correspondence to a linear operator that map elements of the Lie algebra to another element, Lie algebra like this. So the adjoint representation acts in the linear space of the Lie algebra itself. So that is how the adjoint representation works. Any questions so far? Must be very well known. And if I have u equal to u exponents of f, then this u also can be realized as a linear operator acting on the Lie algebra. Namely, it would put f g into another g, which can be written as a Taylor series, roughly speaking, exponentiating the previous equation. So sometimes we call that using a. So let me introduce the notation, the mathematical notation, because sometimes it's convenient to use it. So it is an operator adjoint with index f, the matrix corresponding to the operator f acting on G. And this I call adjoint with the capital A because it's a representation of the group. So this is the elements of the group. This is an element of the algebra. There you go. Okay, any question so far? Okay, and sometime I also will use physics notation, u minus 1 g of u. It's a more sloppy notation. I'm sorry, u g u minus 1. Okay, so now we are going to introduce the coadjoint representation. So the coadjoint representation acts in a space dual to the linear space of the Lie algebra. So the dual space is the space of, say, this vector. It's a linear space where one can multiply by a constant and add these vectors together. The dual space contains f, and there is a notion of the scalar product between one element of the dual space and an element of the Lie algebra. One can think about this as a sum over indices. If the elements of the Lie algebras are vector with upper index, then the dual space would be the a vector with the lower index, a contravariant and covariant vector.
In our example, is it an integration? What's the notion of that you're using?
With the notion of what?
In the example you're discussing, is that
in that example that we are discussing, it's going to be integral over x and p. So in the, but running ahead, if this is a function, it turns out that if this is a function of x and p, then this function is also a function of x and p, and the scalar product is simply integral over x and p, f x and p, x and p. But all this discussion here can be done for a general Lie algebra, general Lie group. And the coadjoint representation is defined so that the notion of the scalar product is preserved. That is, if I rotate both f and p at the same time, the scalar product doesn't change. So let me write it down in the mathematics notation. So the adjoint u, for any u, if I act adjoint representation on and rotate both capital F and small f, then the resulting two vector would have the same scalar product as before. Here, this notation adjoint star means that it's the coadjoint representation. So this is a coadjoint representation of the Lie group. This can be taken as the definition of the coadjoint representation. In terms of the representation of the Lie algebra, that means that the following is true. One can show that the effect of rotating this f infinitesimally and rotating this small f infinitesimally cancel each other. So let me write down a joint used of some G if U is e to the epsilon times G, then we can find this F plus F a joint G F is equal to 0. It is just the expansion of the equation, this equation, to linear order in epsilon, and we have this relationship. For example, we know how if we know the structure constants of a Lie algebra, then we can write the matrices that represent the basis vector of the Lie algebra in both the fundamental and in the adjoint, in the coadjoint representation. So what does it mean? So if I choose a basis, I have, if one choose this basis T of A, so that any elements of the Lie algebra is written as a vector in this with the index upper A in this basis, and if we define the structure constant F A B C T of C, then one can use this definition to find out that the adjoint representation corresponds to putting each of these basis vector to a matrix TAB equal to F ABC, and the coadjoint representation would correspond to putting them in the following correspondence. Each operator, which generator small ta correspond to a matrix F minus F A B C. That one can derive quite easily. And the fact that these are representation can be checked by using the this Jacobi identity for the structure constant of the Lie algebra. Any question so far with that?
The pairing in this example,
the
inner product.
The inner product. So I would so here the inner product would be just Fa times F of A. So with this choice of representation, the invariant scalar product is exactly this one, sum over A. Yes, I have to specify the definition of scalar product, and then use this relation, this requirement to derive the matrix representation of the Lie algebra in the coadjoint representation. Okay. A lot of time when we learn, at least in the courses of group theory designed for physicists, only the adjoint representation. There's no view. For example, when I learn it from books, typical book like Georgi's book, there is no discussion of the coadjoint representation, and the reason is that for many Lie algebra, there is a notion of the scalar products of two elements of the Lie algebra. There is an invariant metric that one can use to lower the indices. So, for example, for the SUN group, it would be a trace of the product of two generators in the fundamental representation. And so, for many cases, we don't have to distinguish between the Lie algebra and the dual space. The two representations are equivalent. But one can check that it's not the case in general. For example, I think if one look at the group of symmetry of the two-dimensional Euclidean space that has two translation and one rotation, then these two representations are different. For compact and semi-simply grouped, these two representations are the same. Okay, in our case, why do we want to talk about the adjoint and coadjoint representation? Why we want to use this notation is that because we want to attach different physical interpretation for the Lie algebra element and the elements of the dual space. So for the Fermi liquid problem, what I'm going to do is to identify an element of the Lie algebra, a function of x and p as an observable. A physical observable, and an element of the dual space as describing physical state of our system, so that the scalar product between f small f and capital F is the expectation value in some sense of the operator of the observable f in the state that is characterized by the function small f. So the distinction here between the space, this Lie algebra, and the dual space is in the physical significance we attach to quantity. For example, if this function f is equal to p squared over 2m, that observable that we are talking about will be identified with the kinetic energy in our system. And f would be state, and the scalar product is integral over dx dp over 2 pi to the power of d. F of x and p, f of x and p is the semi-classical equivalence of writing trace of rho times f, where rho is some density matrix and f is an operator. So here I'm making a classical analogs of the notion of the trace of rho f, where rho is now replaced by the distribution function, and f is the function in phase space replaces the operator acting in quantum mechanics.
But is little f not positive?
So this little f, in order for it to correspond to a state, have to be positive. Yeah, we are going to
subspace of the dual space.
It's a subspace of dual space. In fact, we are going to run ahead. We are going to make sure that this function f has only two possible values, 1 and 0. So we are going to even restrict ourselves to even a subspace of a particular subspace of all the possible state.
So is this supposed to be valid beyond classical level?
This is discussion right now is all classical. There is a way to generalize the discussion to the next level by replacing the Poisson bracket with the Moyal bracket. Sorry, there is one more bracket person. The Moyal, one can do a Moyal bracket and then get more quantum. But I'm not sure whether that actually is a useful thing to do, as I will transmit this confusion later. Okay, so in our case, then the distinction that we make between algebra and the dual space is purely because we want to attach different physical interpretation for the vector in this space. At the level of the adjoint or co-adjoint representation, the formulas are exactly the same. The two representations are exactly isomorphic to each other, and that's because the group of the group of canonical transformation has notion of scalar product of the two element of the Lie algebra. You can check that integral of dx dp of f of x and p g of x and p is invariant under a canonical transformation. That is, if I think about this as product of g and p, f of g, let me write the formula out. If I rotate by Poisson bracket, h f g, if I define this to be the scalar product of two elements of the Lie algebra plus f and Poisson bracket between h and g, this is 0, and one can show that by integrating by part. So rewrite this Poisson brackets its derivative, moving the derivative from acting on f on acting on g, and then you will find that this notion of scalar product, there is a invariant scalar product in the Lie algebra. And so this is what I want to tell you about the co-adjoint representation.
Sorry, is it clear that the coadjoint action preserves this property of being 0 and 1?
The action?
If you apply this coadjoint action on some given state, which is either 0 or 1, after the transformation, is it still like that?
Yeah, so it is. So let's now go to the next topics, which is the coadjoint orbit. Okay, so the coadjoint orbit, let me define the coadjoint orbit. So let us take elements of the dual space. And construct all possible action vectors that is obtained by acting on elements of the group on this F0 with all possible u. So F0 is some vector, and we are taking u and then act on that and consider all possible vectors that is obtained by acting this u on this F0. Okay, so that we call that the coadjoint orbit.
So I'm back to my question. You are using infinite dimensional manifolds here.
So I'm using here my algebra is infinite dimensional.
So that was what I was asking before.
Yeah. I'm sorry. Yeah.
So the measure, you have problem with measure on this manifold?
This is an infinite a volume.
So there is no Lebesgue measure and all that, all these kind of problems?
I don't have the sufficient mathematics sophistication
Since you are going to construct a measure then.
There is a symplectic form, right?
Yeah, construct the
Symplectic
I mean,
form.
the Kirillov-Kostant-Souriau construction is for finite dimensional things. You are extending
Well, maybe we should let him go because he hasn't extended yet anything. Then it's going to be complete.
Yeah, but I'm going to extend it, so that's, yeah. And mathematically, that's going to be maybe questionable, but presumably with some regularization, one can do that. But let's defer that to later. So this is the notion of the space of all this point is the so-called coadjoint orbit. And let's do an example, a simpler example than the example of the canonical group is the group just SU2. Let's consider just SU2 algebra or SU2 group. So for SU2, the adjoint representation is the defining representation of the group SO3. So this is, we have a three-dimensional representation, adjoint and co-adjoint representation, since here there is a notion of scalar product in the Lie algebra, SU2 Lie algebra. So a co-adjoint representation of SU3 is basically rotation in three-dimensional space. That means that the co-adjoint orbit is of a vector that is non-zero, is going to be a sphere. So for SU2 group, the coadjoint orbit is just a sphere. Okay. So let's go back to a more general case and I'm going to do the following. Now there are two ways to think about the Kirillov-Kostant-Souriau form. One that I'm going to present right now is not the original construction, but it is quite simple from the physics point of view. Let us first think why this is useful for the problem of Fermi liquid. Suppose I now construct the coadjoint orbit using first I use the group of canonical transformation. As my group. Second, I'm going to take the this state F0, the initial vector, to be the ground state, isotropic ground state, that is F0 equal to 1 when P is less than Pf, and 0 when P is bigger than Pf. So one think about this as I draw on the previous lecture, some kind of a tube in higher dimensional phase space. So here, if this is Px and Py, it would be a sphere in Px and Py, and then extended infinitely in the x and y direction. This is my F0. And then we are going to act on that, the elements of the group of canonical transformation. Since canonical transformations are result of a Hamiltonian evolution, as we explained at one point, using a function in phase space f of x and p as a Hamiltonian, then this evolution preserves the phase space volume, and that means that if we have a point that has f equal to 1, and following it in these Hamiltonian evolutions, the surrounding region will always have f equal to 1. The Fermi surface remains sharp under canonical transformation. And so this is the way that we are going to parameterize the Fermi surface. Namely, I'm going to, instead of introducing all this height function, etc., we are going to parameterize our Fermi liquid state by saying this f is equal to the result of acting on f0 elements of the group in the using the Coadjoint representation. So that's the that means that the state of the Fermi liquid is now form a Coadjoint orbit. This is the dynamics will be the dynamics on that Coadjoint orbit.
This transform therefore that different energy, right?
It transforms a state into a state with a different energy. Yeah. But it is a way that we are going to parameterize the different state.
So somehow every state, I mean, it's not true that every state that is just 0 and 1 is in the Coadjoint orbit. I mean, because there's conservation laws. And
it's a conservation of only a particle number that we have to preserve. So,
but isn't the topology somehow conserved?
The topology is conserved. So we can show that for a small perturbation. So if I have a small perturbation around this state, then it all can be parameterized this way. We can relate the U with the shape of the Fermi surface. But there are more. I cannot make a statement about large deformation. Presumably there is at least a finite region in this amplitude of the perturbation that one can parameterize this way. But the state in which the Fermi surface is broken into two pieces at some point, that is not going to be cannot be parameterized by using this parameterization.
But all the ones we're interested in are in this.
Or the one that maybe a subspace, because in condensed matter physics, some people are interested in the phase transition in which the Fermi surface is broken into two, and that formalism is not going to describe that. But all the state that the classic Landau theory of Fermi liquid described can be done this way.
Can you see again what this U is? This is not your Hamiltonian of your system.
It's not yet a Hamiltonian. It's just a way to parameterize the field.
I'm not sure if I completely understood this thing. So is the statement that all of the physically interesting states that we are going to care about are members of the same orbit?
Of the same orbit. All the states that can be obtained by acting on the ground state with a smooth, external field, electromagnetic field, is going to be a member of that points on the same Coadjoint orbit.
But then, is it possible to simply characterize these states as functions of x, y, px, and py?
Yeah, but I'm going to reduce it a little bit later as I'm. Now do
So I want to suppose that now, so U is going to be e to the g.
Yeah, U is going to be exponents of some function of f.
So if g is very small.
Yeah.
Yeah, or phi or whatever.
Yeah.
Phi.
That's a function of x and p.
So maybe it would be helpful if you wrote what f is for such phi.
Yes, I'm going to write it down. Yeah. Yeah, I'm going to do it. maybe I will do it now. Once the question arises. So, F. So for u equal e to some function of phi, in the sense this is not exponents of function, exponents of a generator of a Lie algebra that is correspond to this function. The function f is equal to f0 plus a Poisson brackets of phi if f0. So f0 is theta function of pf minus p. And this is a Poisson bracket. Poisson brackets mean df d phi over dx dot df0 over dp minus d phi over dp df0 over dx. But f0 is chosen in a way that it's x independent, the distribution function, so only the first term survive. d0 over dp is delta function minus unit vector pointing in the p direction times delta function of p minus pf. And here I have df of the times d phi over dx. One can rewrite it in a more better way like this: p minus p hat d phi over dx minus p. That is expanding this theta function. One get the in power series over phi. One gets this correction. As promised, the distribution function still has the form of a step function, except now the step function happen at a disturbed Fermi surface. So let me draw it right here. So this is the old Fermi surface, and now we have a new Fermi surface, and the change on the position of the Fermi surface, let's say this height function is called u. U at the position of theta and x is equal minus p d phi over dx evaluated. Now I have to evaluate it at p equal pf. That is where the delta function lives, and and at this angle theta. So yeah, the vector p has this angle theta. So how do I say that? How do I write this? P is equal pf times the unit vector that point in the direction of theta. Where phi.
Some Legendre transform or something?
It's not a Legendre transform. It's just phi. It's not a Legendre. P.
The case that for any u there exists a phi which so that you can obtain u by this formula.
You can integrate this. So since phi now phi is determined not uniquely. Actually, one can just solve this equation, and then reconstruct phi out of U.
But this equation is only applicable for small phi. For larger phi, it would be much more complicated.
We would have a second term.
This is the first order phi.
That's the first phi.
Could you claim that all of them can be reabsorbed into the step function?
All of them can be reabsorbed into a step function, as by the argument that I gave.
No, but this was only a linearized version.
It's the argument is that the Hamiltonian evolution is volume preserving preserve the volume in the phase space, and so the distribution function, the evolution of the distribution function, where we can think about that as a flow in phase space, and if you have a point inside the Fermi sphere, it will going to be always inside the Fermi sphere, and because of the conservation of phase space, the distribution function always 1 in the vicinity of that point.
So the density is never changing?
Density
of a point, if we track this point,
if we follow
the point, it's never changing?
It not change, it doesn't change. But the place where the distribution function jump from 1 to 0 changes.
To my knowledge, this Liouville theorem is valid in finite dimensional case. I don't know any analog in infinite dimensional case.
Which
The
theorem?
preserve of the volume in phase space.
This is a finite dimensional.
This is a finite dimensional phase space. Yeah, so we are somehow jumping back and forth between finite and this is so this, how would I say, the space of all, so the dual space is infinite dimensional. Each vector is a function of a finite dimensional space. So the dual space is the infinite dimensional algebra, but each vector is a function in 6-dimensional space. And the claim is that the coadjoint orbit of the initially chosen function that is either 1 or 0 contains only function that satisfied. So let me write down this condition: f squared equal f is the constraint that preserved under canonical transformation.
I would like to make a comment because there are a lot of complaints about mathematical rigor, but correct me if I'm wrong. Even though you're using all this infinite dimensional intuition and so on, in the end, whatever relations you're going to derive using this intuition, they can actually be checked. So if someone is unhappy about the rigor, they should just check the final equation. The final equations are going to make sense independently of.
Yeah,
there are going to be some PDEs.
It's going to be, it's going to satisfy my own and maybe some physicists.
But yeah, just view it as an intuition if you're unhappy.
Let's go along this line, at least because we are going to try at the end to reproduce Landau's Fermi liquid theory. So that's going to be our next task. Yeah.
So you can see that the integral of u is 0 just because it's a total derivative in x. That you're trying that you want particle total number of particles, the total volume to be preserved in some.
Yeah, the total is just because here we have yes, basically this one.
And in the concrete example,
you have to integrate over the whole space.
So you also integrate
over x. So basically, this the theorem that we are using is that for where we have functions, the integral over phase space of the Poisson bracket is equal to 0. So that means that this one contributes 0 to the total density. The coadjoint orbit, I forgot to say, can be understood as a coset, and it's rather simple to understand this. There is some members, there are some subgroup of of our group that preserve F0. So acting that subgroup on F0 doesn't move us from the point F0. So the coadjoint orbit is a coset between our big group, let's call that G, and the smaller group H, and the group H is the one that map F0 to F0. In our previous example with the group of SU3, you can see that this group G is SU3, the group that preserve the point, the rotation around the vector F0, so that is U1. And so we get the sphere, the coset of SU2 and U1.
Can I think of this construction intuitively? Because this F function, if I use this fermion description, is essentially a fermion bilinear, where the fermions are kind of half Fourier transform, which is kind of the degree of freedom is like the particle whole pair. And this is just the usual coset construction for this kind of object that is like this fermion bilinear. I mean, you cannot do it because it's not a boson, like for ordinary symmetry breaking, but is this the right intuition, or?
Perhaps, yeah, I'm not used to think about that. Clearly, this function f is a Wigner, related to the Wigner function. Yeah. Any question so far? So the fact that it's the coset means that there is some redundancy in this function f. This function phi. Not all function phi lead to different state. There are phi's that lead to the same state. And let us first figure out what is the stabilizer group of our chosen F0. So let's try to define the stabilizer group. So again, we are doing that for small phi. For small phi here, the P d phi over dx is equal to 0 when P is equal to Pf. So inside this stabilized, so I'm going to one choice that is not the most let me see. So I'm going to one choice that is I think is stronger than we need. So these two require phi equal to functions that vanishes on the Fermi surface. Okay, so for these functions, since they vanish on the Fermi surface, the derivative over x evaluated on the Fermi surface is also vanishes. Okay, so there is at least a sub group of the stabilizers that parameterized by function that vanishes on the Fermi surface.
So I thought it was the normal derivative. It's the tangential derivative.
That's the derivative in the x direction.
Oh.
The component of that in the normal.
Yes, so derivative in the x direction, but I'm any function.
This is much stronger though.
It is a stronger. So there is a subgroup of this group of stabilizer, but I can use this to fix a gauge. I can use this to do a gauge fixing. That is, gauge fixing here means simply that I have a function of x and p. I can to now working in linear order in this alpha. Here, everything we are working in the vicinity of. So, gauge fixing here means that if I have a f and I just multiply that by some elements of the stabilizer group, when I multiply that, I get phi plus alpha plus some 1/2 of phi alpha by Baker-Hausdorff, right? This is basically this exponent to linear order. It just becomes plus alpha. Since alpha has to be 0 on the Fermi surface, but it's free to be anything anywhere, I can use this to say this function is a function of only x and theta, and not a function of p alone. So here I have, if I have a functions of x and p, I look at the function on a certain line in the momentum space. Right? That function has some profile. I can choose the function alpha to kill off all the dependence on the absolute value of p. Choose the function because this I cannot kill the value of the function exactly on the Fermi surface because the function alpha itself needs to be 0 on the Fermi surface. But I can make phi to be a function of only x and theta. So in particular, you can see here also, here this derivative here is the derivative of a function evaluated on the Fermi surface. It knows nothing about the function inside the Fermi surface. So the stabilizer group basically are the canonical transformation that reshuffle points inside the Fermi surface and not touching the shape of the Fermi surface itself. And this co-set that the coadjoint orbit can be parameterized by only a function of x and theta. Then at least one can gauge fix the theory that way. Now let's.
That's not too surprising. I mean, even to the whole story of coadjoint orbits, but if you want to get deformations of the surface, that should not just be a function of the depends on the positions of the angles.
Yeah, but here it is some expectation that we have also in the in 1+1 dimension. 1+1 dimension, there's the Fermi surface has only 2 points, and here that means that we need only 2 scalar fields in order to parameterize the shape of the Fermi surface. In the case of higher dimension, then we need an infinite number of fields. This is how it appears. Okay, so last 10 minutes, I'm going to write down the central object of this construction, that is the Kirillov-Kostant-Souriau form.
By the way, is phi the boson in your title? The bosonization?
It's the boson, yeah. is that infinite number of bosons on that we formulate the Fermi liquid theory. Okay, so now we need to, so we have following things. We have a system. Our system is parameterized by, is basically the evolution of our system is a trajectory on the coadjoint orbit. Right? When the Fermi surface changes its shape, it's moved on the Fermi surface. So it's some kind of function of f as a function of t. It can be, if we start with the system in ground state, that starting point would be f0, and then it moves. And we can think about this as parameterize it, as we said, as a adjoint u of t times f. Right. So we need to write down an action. This is of action as a function of f of t. But I'm going to write it as a part of this part of the action as an action as a function of u of t. And then I need to check that u of, when I take u of t and replace that u of t times some g of t, where g of t always is in the stabilizer group H, the action doesn't change. And that would be my, then it would be my good action. So part of the action is the Hamiltonian. And we are not going to discuss it. It's given in Landau theory, energy of a field, some region of a Fermi space. The non-trivial part is the part that has one time derivative. That the part that eventually associated with the symplectic two form. So I'm going to write this term like this: f0 u minus, I think here I have u minus 1 dt u. Okay, that is my okay, so let's check that it's so the non-trivial thing that we need to check is that this one is invariant under such a kind of change. Okay, so let's do that. So if I do a transformation, so I'm going to do g, so it's going to be g minus 1 u minus 1 dt u minus u times g. This is, so first of all, let's check that this makes sense. This is an element of the Lie algebra, and this is the element of the dual space. So there is a notion of the scalar product f0 with that. That's always one can define. Now suppose I have I make this change, then I do that. Okay, so here there are two terms. One term is when t acts on u. So that term can be written as a adjoint g minus 1 acting on this u minus 1 dt of u. Right. And this term, by the definition of the coadjoint representation, this becomes adjoint star with a minus sign, adjoint star of g minus 1 acting on f0 u minus 1 dt u. Right. This is 0 because the how would I say, this is, well, this is not 0, it is equal to the previous sorry, this is g, sorry, this is acting on g. You can I use the fact that I can rotate both of these using G and then get back this G. So that is equal to F0 u minus 1 dt of u. So there is no problem. This part simply say that there is no change in the Lagrangian. The non-trivial thing is when this dt act on G. So then it becomes F0 G minus 1 dt of G. Okay. So here there must be a way to show that more elegantly, but what I was doing, what one can do is to say if G is an exponent of some element of the algebra G, where G here is the algebra of the stabilizer group. This one can be written as F0 G dot plus F0 G dot plus dot dot dot. There's a whole this Becker-Hausdorff expansion. All the term beside the first one is 0 by the condition that this F0 is invariant under the action of the Lie algebra G. So for example, this term is equal to minus G F0 G dot. Well, and it's F0, since it's an element of the G is the element of stabilizing algebra, this is 0. First term is a total derivative, you can show. So the algebra, this term turned out to be the Lagrangian density is not invariant, but the action, but it's a total derivative. Okay.
So is it not the case that if capital G is in the Lie algebra for all t, then also its standard is in the Lie algebra? So
sorry?
Isn't the first term also 0? Because if G is in the Lie algebra, capital G is in the algebra for any t, then the time derivative is also in the Lie algebra.
Yes, but the scalar product of F0 with the element of the Lie algebra doesn't have to be 0. A scalar product doesn't have to be 0. It is the Poisson bracket is 0, but the scalar product doesn't have to be 0. It is actually like a physicist messy way of writing a more elegant construction, which is the integral of dt ds. If we introduce, as in the Weissuminer-Witten action, an extra coordinate that runs from 0 to 1, this term can be written as scalar product of the following object: the scalar product of f with the Poisson bracket of u dt u minus 1 u ds u minus 1. I'm not going to show this. It's rather straightforward to show this equality. And this is the Kirillov form. Okay. Kirillov-Kostant-Souriau symplectic form. Or more. Let me define it in the way that mathematicians usually introduce this form. So we have this coadjoint orbit, and let's choose a point F. symplectic 2 form is an object that map 2 vectors into a number. So these are 2 vectors, this delta f1 and delta f2. We map it into a number by saying that we go from f, we can go from f to f delta f1 by let's say delta f is an infinitesimal vector, then it can be generated by elements of the Lie algebra f1, right? That going from one point in the coadjoint orbit to the next point is generated by an element of the Lie algebra f1. And then f2 take us from f to f plus delta f2. And this form, Kirillov-Kostant-Souriau form, is defined as the scalar product of the vector in the dual space with the commutator f1 and f2.
So that's not an f naught.
It's not an f naught, but f is equal to u, roughly speaking, u minus 1 f naught u something. You can actually shuffle the f, the u from one side to the other. Okay, maybe I'm running out of time, but this is the way that one can write down an action. The meaning of these terms is very roughly, one can think about that as some kind of a Berry phase when the Fermi surface changes its shape. Like Q dot is a Berry phase when we go from one wave bucket concentrated at P and Q to a next wave bucket at P and Q plus P plus delta P, Q plus delta Q. I'm not sure if I can define this, I can rigorously define this notion of the Berry phase. But what we are going to see next time is that this leads us to the same equation of motion as the equation of Landau's Fermi liquid theory. Clearly, this symplectic form here is a very natural object in mathematics, and it's using that we will get the equation of Landau's Fermi liquid theory.
H is some arbitrary. H here is some arbitrary.
H is a Hamiltonian. That Hamiltonian needs to be specified, and if we match that with the way that we can write the general local functional of f, local in the sense that it's local in space, but maybe non-local in momentum, and that gives us the Landau parameter.
Is this somehow unique? I mean, this
construction.
Yeah, this action you chose.
To the term with first order in time derivative seems to be unique in the sense that I don't have a different example that I can write down, but I don't know how to prove that it's really a unique closed two form. Okay, so it has a nice property that this let's say
The moment you bring in a group of diffeomorphisms and you demand that everything is invariant under this group, then
no, this term is invariant under this global diffeomorphism.
Indeed, then it may be invariant. But if you just say, well, let me find some symplectic form on the space of surfaces, I think there's a ton of symplectic form on the space of surfaces.
Yes, this demand, I'm not sure whether one can make it because the Hamiltonian part is not invariant under diffeomorphism. There's a global diffeomorphism invariant transformation. So for some reason this part is invariant. It's not. It encodes some information that is not dependent on the precise dynamics. Some kind of information about the Hilbert space of state.
The only place here where it was important that you were dealing with the Fermi surfaces in this choice of F0.
Yeah.
Let's say I have some like plasma with like uniform distribution in the initial state. It would seem that you can apply this to. It seems like a very general.
Normally, if I have a initial distribution that is not a sharp function, then we have a very the stabilizer group is much smaller, and so we need much more degree of freedom to parameterize the perturbation. So you need to specify not only the place where the Fermi surface is, but also the shape that the distribution function changes from 1 to 0. So then this situation will get many more degrees of freedom.
Still, if M0 is a thermal state, this is well defined?
Yes, but I don't know if one should expect a Lagrangian formulation of the dynamics of finite temperature plasma. In this case, because at the end the system will dissipate energy, and so it's probably to be conservative, we can start with zero temperature situation first.
Here in this action, do you think of U as these gauge-fixed functions with only like support on the boundary, or just the full thing?
Well, you can be a full thing. So this action is invariant, well, up to boundary terms to any transformation where we multiply U on the right by elements of the stabilizer group. So any function. Any solution to the equation of motion can be we can multiply any solution by a G that is a member of the stabilizer group.
Sorry, the symmetries of this action, is it the full group of canonical transformations or only the stabilizer?
So the action doesn't this one is invariant under, let me try to be precise, all the
there, it's invariant under U goes to U times G.
Let me see. If I have an F, let's say if I have an F that is a function of T, then the action is this Wessumino action is invariant under multiplying by a constant member of the group by acting on that with a member of group that does not depend on time. That's what I mean. You can do a global transformation, and that will not change.
Maybe we should first of all thank Sean, and then we go to the question session. Let's do things in order.
Thank you.
Let's have a few questions, and then further questions are going to be in offline. Yeah.
So should we think of this as a derivative expansion, or is the term with one derivative the only one that is
The one with a single derivative?
Yeah, so I'm asking, would there be additional terms if we go to higher order in derivatives? Is it, or is this the full step?
So with this term, when you expand it, because this here, it's when you write it down, there are Poisson bracket, etc. There will be term with higher derivative when we expand this out. If we stick with the term with two fields, so the quadratic, so when we next time we will write this a quadratic term has a d phi grad phi. At the quadratic level, there is only two derivatives. Presumably, there is a term that one can add to this that has that can have more derivatives. So this is presumably the term with lowest number of derivatives.
So in general, one could try to add the higher time derivatives.
That for sure. If you want to add terms that have higher space derivative but only one time derivative, that's also an interesting question, but I don't know the answer. I think there could be terms like that.
Quick question, I don't understand what exactly we achieved. So in the previous lecture you criticized Landau theory, saying that it's not clear where it comes about. Mm-hmm. And then you also criticized previous attempts trying to build effective field theory, saying that they fall short.
Mm-hmm.
Now
we have
you found some natural symplectic form, and it seems that in the end this is going to reproduce Landau's equations, but this is still Landau's equation. So what have we achieved? And we still didn't understand where why is this a good effective theory. We didn't understand why the previous attempts by Polchinski and Sakharov fall short.
But we know how to write down at least a standard field theory in the sense of an action principle. So if there is any truth in this, we haven't been able to derive this from microscopic theory. Yeah. But if there is a truth in it, we just say that this is, now we think about this as an effective field theory. So we have, this Landau theory is going to be the first terms in the in this derivative expansion. In fact, already here we have terms that have quadratic and interaction terms. We can look at the interaction term and see whether they are, in how many dimensions they are relevant. If they are relevant on why Landau theory works, we can understand if Landau theory works just because interaction terms are all irrelevant. So all this philosophy of effective field theory is like power counting, symmetry, and then hopefully if we can compute loop graph and then see how we can proceed as if it's a normal effective field theory written in terms of inaction.
But when you do this check that it's a good effective field theory, somehow it should play a role that it's a very special symplectic form, the KKS form. Well, we agree that there are infinitely many symplectic forms on the space of surfaces. So where is this? This is not at all clear. I mean, some mathematicians came up with this form for symmetry reasons, that it has to be invariant on the group action. Why is this, if you picked up some other form, it wouldn't be a good effective theory? This is not at all clear.
That is not, I'm not sure I have an answer to this question. I know that at the level of the effective field theory, the term that I can write down, they all have higher derivative than this.
Can I think of phi as like some kind of pseudo Goldstone that is where the symmetry is explicitly broken but very weakly, and so now there's an action which is essentially determined by Goldstone's theorem plus a small correction due to the explicit breaking. I mean, because you don't have full diffeosymmetry because you have this H, but somehow that's supposed to be a small effect, and then there's also kind of a symmetry breaking going on. Kind of like the Schwarzian and all of that kind of thing.
Yeah, so yeah, it feels like that, but I don't have a good answer to Slava's question. Why this? This is basically, we have a way to parameterize. We have a nice way to parameterize all the space of the field configuration, that's for sure. But somehow here we are saying that if we write down this simple action, then we can use it to treat the theory. So in 1+1 dimension, actually this program can be done, and we can check that this actually is the correct bosonized action that one can obtain by another way, by a different way to bosonize the Fermi liquid, that is to directly map the fermion operator into bosonic operator. Maybe I can show you next time. Doing this in 1+1 dimension gives us the standard bosonization that's enforced. And for higher dimension, there's like various nice things that one can see, but I don't have a satisfactory answer to Slava's question.
You mentioned you are going to do some counting of relevance, irrelevance.
Yeah.
I guess that's with respect to some scaling symmetry.
Yes.
Would it be the same as Polchinski's case, or?
So I can show you why it's better than Polchinski in the following way. This phi, we are going to show next time that so here there is a Landau parameter f of p in p prime, and we see that this part of the Hamiltonian is quadratic over phi. So we have this times some phi squared. So it's a part of the Landau parameter is part of the quadratic action. While in all the previous, including Polchinski or Shankar, etc., treatment of the Fermi surface, one have to do a sophisticated power counting to see that it's very non-trivial power counting to see that this so-called forward scattering described by this is marginal. So the power counting gives you the fact that it's marginal, not even, and then only explicit calculation will show that this coupling constant does not run at all. And it's not even clear whether that's why it's so. Yeah. So the power counting here make this Landau parameter not running by default. Default because it's part of the quadratic action. Yeah.
Okay, well, thanks, Sean. We are looking forward.
Thank you. Sorry.